Thank you very much. Again, my name is Jesse Martinez. So today we're just going to kind of go a high-level overview of how Los Alamos has deployed most of our networks using RDMA technologies for various aspects of both MPI communication as well as data movement. As you know, HPC systems generate a lot of data. They also need a lot of fast, high-speed networks to generate that data, and then we need to be able to move it off the clusters in a timely manner. So Los Alamos has a very difficult challenge to kind of integrate all our different systems that we have and kind of converge them into a single place where we can store the data and then move them to the different tiers that we have for storage in Los Alamos and then move them elsewhere to wherever they need to go. So again, just a quick introduction to how Los Alamos deploys our networks, how we use it in production, and some of the challenges that we have with trying to deploy these fabrics in an easy way to manage them. And then on top of that, how we actually administer them and monitor them for any issues to keep them optimized. And then we want to try to expand that into the future with new technologies, learn from our mistakes, grow from that, and adopt some new technologies and software that people are developing to make our lives a little bit easier. So again, just a quick introduction to what Los Alamos does. So we have a very diverse range of networks. Our users have a wide range of jobs that they want to run on our systems, ranging from simulation to calculation to whatever you can think of, that's what they do. So we have to generalize a lot of these systems enough for these users to be able to make it useful for them, at the same time make it easier for us to maintain the software stacks, deploy them in a timely manner for them, do maintenance on them whenever we need to without impacting them too much. So there's a lot of work that goes into trying to making sure these fabrics stay up for them as much as possible without having to impact them on a daily basis. So we have systems that range from old legacy hardware that's slowly going out the door. This is all old InfiniBand, QDR, FDR fabrics that a lot of our users still make use of just because of some workhorse jobs that they have. That they don't need to expand to too much faster technology, but they do have a lot of workload that is relying on some older hardware and software that they want to make use of. As well as new systems that we're deploying within the past couple of years, then new systems coming within the next future outlook of what is out to come. So again, a lot of our jobs range from MPI parallel-based codes to GPU computations that they have for some of their simulations, for visualization, different aspects of that, interactive tools that they use to generate and visualize their data. So we need to make sure we can develop these clusters in a way and have the variety of these clusters to make use of them for that. And then on top of that, these users generate terabytes to even petabytes worth of data on most of these systems that we have. So it's very hard to kind of make sure we can have all these users using the systems at the same time making sure we can aggregate their data and move it off the system for them to do their analytics, and then recall that data back in a timely manner that makes it easier for them. And then finally, just making sure that storage is available for them, making sure we have the capacities for these users today. We're trying to make our users a little bit more knowledgeable on how to make use of our storage systems and why the networks are designed in this particular way, so that they're not just storing all their scratch space into archive and tape and things like that, which makes it hard to recall with that kind of size of data, but training them to actually utilize our networks and our storage systems in a way that is useful for them. So here on the side, we just have a few examples of the type of systems that we have. So again, Trinity, which was just deployed within the past couple of years, is our largest system now that we have with the labs. Over 19,000 compute nodes today. It is a Cray-based system, 2 petabytes worth of memory, and it has the capability of 42 petaflops of calculations that it can do. And then with that memory offload, we need to be able to get that data off that system into a separate file system that we have for it today. That's Cray Aries Network internally for that. And then some of our smaller commodity technologies are a little bit smaller than that, 1,500 nodes. The memory size is only in the terabyte range, but it can do a lot of calculations as well too. But those are made up of both Intel OmniPath and EDR Mellanox today. And then our storage solutions that we have for them range from different types of tiers, which we'll go over shortly as well too, ranging from just their home-end projects, which is kind of NFS based today, Ethernet on that side, ranging to Scratch, where we need to be able to move the data off quickly. So that's InfiniBand used with Lustre today. Campaign storage is a new type of tier that we developed in Los Alamos the past couple of years for just kind of maintaining a short-term archive, you can say, of their campaign use on the system. So generally have about a year or two of work that they have dedicated time for to do it on the systems. And so that campaign storage is meant for them to recall a lot of their data that they've been doing within that campaign but also kind of keep it as an archive type system so they don't have to recall it too often from scratch. And then finally, the full archive that we have for long-term storage. We have data going back to the 1950s at Los Alamos, ranging from disk to tape. So we've got to make sure we can recall that in a timely manner as well too. Specifically, the type of fabrics that we have at Los Alamos, again, Mellanox is one of our biggest ones that we have. We have up to EDR today, but as I mentioned, we have still back going from QDR just with our older systems. We make use of UCX for a lot of our MPI communication on our Mellanox systems today. We recently just upgraded to that within the past couple of years. We've been using some of the upstream Red Hat communication still. And recently just moved to UCX on our newer Mellanox clusters. We also make use for it for our SAN network, our storage area network. That's where a lot of our storage systems live today, primarily Lustre today, but also campaign storage. And then we use that network as well too to make use of the archive for the long-term storage as well. With these types of fabrics, we have dedicated subnet managers. That's primarily used for our monitoring infrastructure, which we'll go over in a few minutes as well. This is mostly based for us to do offloading with the subnet manager, with use of the perf manager for us to gather counters and all that. But also we have some redundant subnet managers on the fabric as well too, just for redundancy if we ever need it. And then our topology ranges from mostly fat tree topologies, the fully fat tree, to range with our SAN network being a dragonfly topology, which we call the damselfly. For those who have been attending the past couple of years, Susan Coulter did a presentation on that and how we developed our damselfly topology for our Lustre networks, mostly to make use of fine-grained routing, which is a Lustre a networking utility that you can use for isolating traffic on certain types of network, and that gives you the granularity of isolating that to hardware as well too. So our topologies are made up on a dragonfly where we can isolate the Lustre traffic to certain groups and access that data within those groups without having to have a full bandwidth use on the fabric itself. Our newer systems make use of Intel OmniPath. Today we use PSM2 for a lot of our communication. Those range from fat tree topologies as well. For the most part, we have a range from full foot topology as well as 2-to-1 oversubscribed. That was one of our works with our vendors to kind of get that tested out and going, just because a lot of our users aren't fully using the clusters all the time for a lot of their data needs. So we didn't need to have full bandwidth for the whole entire cluster in general, but we are doing a lot of case studies today to see if that is still a viable solution for a lot of our user workload today. Or if we need to go to a full fat tree solution to kind of maintain that overall aspect of full bandwidth. But you'll hear a presentation later this afternoon about some of the tools that we're developing to kind of analyze this 2-to-1 oversubscription and how it's affecting our user jobs, performance, congestion, how we can kind of track their usage on the network to see if we need to change our fabrics in the upcoming future. And you'll hear more about that later on. Again, these fabrics have dedicated fabric managers as well too, for our monitoring needs and redundancy as well, that we make use with on the cluster as well. And then finally, our last one is just the Cray Aries network, just to mention on some of our Cray systems that we have, but won't go too much into that. Our production design and how we designed our network overall. Again, all the supercomputers themselves have an internal high-speed network that they use, either IB or OPA. But our biggest challenge today was to try to get that data off the cluster into our storage networks. So that's kind of our main focus of this presentation, is to see how these networks were designed, how we thought about the approach of how do we need to allocate as much bandwidth as we can, and have enough redundancy as well too, to make sure that the data can be moved off the cluster for other users to make use of them as well. So we need to be able to analyze what kind of data movement we actually needed to be able to perform these large-scale simulations within the amount of memory that we have in the systems themselves, and be able to move that data off in a timely manner. So a lot of analytics goes into how we look at our users' use case on these systems to see what kind of data they will be generating, other users that need to interact with the system as well too, what their use case is, and then kind of doing a balance between that, and then kind of figuring out exactly how much bandwidth we need to be able to move that data off within a timely manner. And we have some high calculations that determine exactly what that number is based on the type of system itself. And that's mostly just for moving the data off the cluster. So again, we look at kind of the high-speed bandwidth needs we need to have there. And then once we get it off the data, how we can move it between the different tiers of storage that we have. So our biggest use case today, again, is the amount of memory that we need to have. We have a technology called burst buffers that is used on some of our systems just to kind of offload checkpoint and restarts on these systems for quick reinstallations of their jobs if needed. But the biggest data movement is from these storage tiers here to get down to scratch, to get it off the system as soon as we can onto a disk-based system. And as mentioned today, that's mostly Lustre that we use for our scratch space. And those ranges from a few petabytes to 70 petabytes worth of storage that we have for some of our larger systems. So the SAN network needs to be able to handle that kind of bandwidth. So we need to design it in a way that can make use of our data movement, get the data to where it needs to go, and make sure it's resilient as much as we can make it. There's a few ways to do this. Again, the chassis solution for a big SAN network would be the easiest. Benefits of that is you can just kind of throw it in and it kind of works. Everybody can talk to everybody as much as they want. The downside is it's not cheap though. It's kind of hard to be building these networks every single time there's a new generation of hardware that comes out that we need to have those capabilities. So how can we design it in a way that is verbose enough for it to be kind of a stable network at the same time as things need to be upgraded, and we can kind of do it in pieces to make use of the new technologies that are coming in. So we want to make sure we can handle both those kind of aspects. The biggest challenge today is that we have a lot of different storage solutions at Los Alamos. A lot of them being Ethernet today, archive and NFS for some of our home and projects and archive use, Scratch and Campaign again being IB. How do we make all these different types of fabrics and technology, network technologies, be able to communicate easily in a timely manner? Also planning for what isn't going to be the next network that we need to provide for offloading from our clusters and planning for that. So our biggest use case today is what we call our data transfer nodes. These nodes are meant to be able to communicate between all these different networks to be able to move the data off the system and making sure that it can do it again in a timely manner. This is where all the users log in to kind of move their data back and forth between the cluster storage where Scratch is, to the archive, to Campaign storage, et cetera. So they need to understand how these systems work and be able to communicate across all these fabrics as well too. At the same time, again, providing redundancy. We talked about how we make use of Lustre's fine-grained routing for a lot of the resiliency and performance stuff with Lustre, pertaining to Lustre exactly. But at the same time, designing our underlying network as well too to make sure we can give the full bandwidth for the fine-grained routing as well too. So with that, within the next slide, you'll see how we kind of deploy that. But we have multiple what we call IO nodes or LNet routers for Lustre talk to provide these paths to the different fine-grained routing groups from each of the clusters to be able to get it off in a timely manner and provide enough bandwidth there without having to build the back-end storage network to be a full fat tree. And so that's been very beneficial for us to design our network, what we call the Damselfly topology, to be able to fit around fine-grained routing today. But again, the challenge is that we don't know what the next storage solution will be, if it'll be on IB, Ethernet, et cetera. So the Damselfly gives us enough redundancy to upgrade the different tiers of the SAN network itself. If we need to upgrade a certain use case for the Lustre network in general, we have that granularity to do that. But overall, our whole SAN network is based around Lustre today, but we don't know if that's going to be going forward anytime soon. So here's kind of a high overview of just how our networks are laid out. We took the best approach. We thought that we have this whole storage network, the Damselfly, located here in the big cloud there. And that's where a lot of our storage solutions are today. We have multiple Lustre file systems that we have on it. We have multiple clusters that connect into it. And so we need to be able to provide all that bandwidth for that. Some of our high-end clusters like Trinity has its own dedicated storage. So we need to define capabilities to get from that storage system to the rest of our Lustre infrastructure, as well as where Campaign is, and some of our archive that lives off in the Ethernet world up there. And so we put a lot of work into developing what we call these IO nodes or LNet routers for making sure there's enough bandwidth for moving that data off. Our clusters need to be able to design a way to fit into those fine-grained routing groups as well too. So we work with our vendors to make sure we can provide enough bandwidth off that cluster to fit within our storage network today, as well as designing our own kind of Ethernet and high-speed network routers to be able to move data between the IB world and our Ethernet campus that we have up here. Today, those are mostly just media converters. We use IP over IB to move data off into the Ethernet world, and they're mostly just running OSPF today to be able to provide network capabilities from the Ethernet world to this back-end layer 2 network over here with IP over IB. And then our FTAs were designed to be that data movement aspect for all of this here. So we give enough bandwidth to these FTAs here that live on the IB network so they can be able to talk to this campaign storage that is directly connected to them for a fast use case, and then as well as the rest of the IB network as well too. And at the same time, using the OSPF routers to be able to get to NFS and archive. So FTAs are kind of our beefiest systems that we have today to have enough capabilities for our users to get onto those, move data back and forth between those tiers. So, but with that, our biggest bottleneck today is our FTA nodes that we need to kind of take a look at and see how we can expand that to be more useful and cross these bridges of these different topologies that we have coming in the forward within the next few years as well too. So all of this is all designed around the aspect of this backend network. Again, InfiniBand today, but again, what's coming in the next couple of years and what we need to look at going forward. Then our clusters themselves are just isolated networks there, either IB or OPA today, and then using those IO or ALNet routers to get the data off that network there. So how do we administer these? We talked about these a little bit. So with all of our multiple networks, we have separate subnet manager systems designed for each one. These are separate servers that we can actually use to run OpenSM, where we can query the perf manager for logs and all that. Same with the fabric manager. Again, if you've been attending the past couple of years, we've talked about the first one, IBMON, which was something that Susan Coulter designed a few years back to kind of interact with the performance manager with OpenSM to gather counters and errors from the fabric and then report it in a human readable message to a lot of our operators who are there 24/7 to kind of maintain the fabrics, keep them running while we're not there over the weekends and nights and throughout the day as well too. HSMON was developed a few years later by Susan and myself to be the equivalent for OPA. So it kind of roughly does the same thing, just with OPA logging into the Fabric Manager and Performance Manager there as well too. You'll hear about, again, coming within our next presentations as well, of how we've designed HSMON and how we're making more improvements with it to have more granular data and information within the OPA fabrics to get more use cases and do some more studies with our OPA fabrics. As well as some other tools that we developed. Susan developed this as well too, dead gateway detection, which is an automated tool that we've developed to kind of interact with our clusters and take a look at the overall routes from the cluster itself to the rest of the SAN network. So there's a lot of checks like making sure that the IO gateway nodes are up and functioning. We're not getting any packet loss, analyzing the routes within the cluster, analyzing the routes external to the cluster. So this kind of does a lot of moving around the network to kind of poke around these different aspects and making sure everything is running as optimal as possible. And if there's any degradation from that, any packet loss, this tool has a way to log into the clusters and kind of shut down routes and update routes, both internally and external to the cluster as well too, to kind of reset those routes and take them out until we can do maintenance on those servers and get the bandwidth back that we need. As well as we make use of Sandia's lightweight distributed metric service, or LDMS. There's been a few talks the past couple of years as well too, on how those run on the node, and we do a lot of on-node analytics as well too. So a lot of that runs on our nodes today as well too to get those kind of performance metrics. As mentioned, we have a 24/7 technical support to kind of keep all these systems up to date, and they're constantly monitoring all these different monitoring services today to make sure that all the nodes are up and functioning on the fabric correctly as much as they can without any loss of data. And then we have a lot of real-time performance analytics that we use in production. Splunk and Grafana are two of our main tools that we use to gather all these counters and create alerts for all of our admins as well as our users that we're trying to get data to as well too. Grafana is starting to be developed a little bit more to get more of those analytics for our users as well too. We have a consulting team that wants to know exactly what users' jobs are hammering the networks, what's causing congestion, what kind of users are managing their nodes in the right way, and what users are not. So they want to make use of this tool to make sure we can get the best performance for all of our users and make sure everybody's behaving and sharing the network in the right way. As well as it just gives us an overall view of what our networks look like. We have a lot of dashboards that we've presented in the past couple of years that make use of all these different tools and how they interact with each other, and this kind of gives us just an overall view of how everything works today. And then here's some information on the side, but again, we've talked about it. Past couple years, they mostly just look for all these different types of information and present them to the users and the admins. So what's coming next that we need to plan for? Again, we don't know what the next aspect will be as far as storage, what will be the next cool technology and the most redundant and high-performant cluster or technology or storage solution may be. So we need to be able to design these networks in that way to help behave that. We have a separate institution at the labs called the Ultra-Scale Research Center that's kind of doing some more outward thinking of exactly how these storage systems are used, both with a lot of these Grafana tools that we've developed today. To see exactly what is actually happening on our clusters, the kind of analytics that it's doing, and overall usage, so we can deploy the next cluster in an easy way and the right way as well too. So we have a lot of cool tools coming out of there and research looking at different use cases of different technologies and network technologies as well. And then with that, we have a lot of existing capabilities that we have on site today. We have separate clusters that are mostly used for other type of research like Hadoop type builds and things like that, where they want to make use of other different types of already made technologies as well too. So one of them we're actually looking at today is it's mostly an internal Ethernet cluster, but they want to be able to use maybe SoftRocky for some other use cases as well too that the users are asking for. So again, we're looking at more existing tools that we have today to kind of expand on that, as well as just making more use of all the already made technologies that you guys are developing today on our SAN networks, feeding that into our infrastructure team to be able to look at these different tools that we have and make more use case out of them to make sure we can get the full bandwidth. As well as just how we merge everything together. Our FTAs, like we said, are the biggest bottleneck today. They're the ones moving all the data for all of our clusters and all of our storage tiers. So how can we expand on that, give them more capabilities to have more redundancy, at the same time giving the users what they want as far as moving data and make sure they use it in the right way. And again, how to talk to all of it. So finally, our HPC environment, Los Alamos, is ever growing. We're usually on the leading edge of trying to find these new technologies and design our infrastructure and network in a way to make sure we can get the most out of it. But the challenges are still ahead where we need to be able to plan for these future technologies. Instead of just throwing money at it to make it work, we want to make sure we do it in the most efficient way as possible, making sure the whole team is understanding how this all works and we can all work together to kind of design these networks for not just the networking, but for the storage and the MPI world for our users to making sure that they can use it correctly. And as well as a lot of our effort is now moving towards how do we actually monitor these networks in a more efficient way to give a lot of feedback to our developers, a lot of feedback into our program managers who are designing these new technologies and looking for feedback as to what they need to buy. And so our tools are trying to make use of that today. So, but for the most part, again, it's never the network unless it is, and we try to fix it. So with that, I asked if there are any questions. Oh, your question, yeah.
So I'm assuming your workloads are performance sensitive. So what's more important for you? Is it latency or is it throughput?
Both. That's the hard truth for us today is that a lot of our users need that MPI capability, the low latency for a lot of their jobs, but at the same time they need to be able to move that data and generate a lot of data quickly enough and move it around, things like that. So we have to kind of plan for both. For the most part, it's bandwidth usage today, at least from the storage side. We're developing new ways to look at how metadata is accessed with the low latency, but looking at what the bandwidth needs are, seeing if that still needs to be on InfiniBand today. Ethernet's coming up to speed with a lot of the bandwidth capabilities, but the latency is always the bigger killer with Ethernet. So a lot of the already made technologies are still being looked at for metadata usage and especially on the clusters as well too. So it's half and half.
Thanks. And just another question. You mentioned the usage of SoftRocky. You're looking into it. Mm-hmm. What advantages are you seeing you're expecting to get from SoftRocky?
The biggest aspect is that we have this cluster that is doing a lot of futuristic research and development, but it was all built with Ethernet technology today. So a lot of the hardware, if we wanted to do HardRocky, a lot of the hardware would need to be swapped out. If you wanted to use more already made technologies like IB or OPA, a lot of the hardware would need to be swapped out. So trying to use the existing technology today, SoftRocky was one of the options that would be an easy feature to kind of deploy there and test out. So,
okay. Thank you.
Yep. Anything else? All right. Thank you very much.